Okay, we can get started. Good morning. The handouts from yesterday is still the same. I still have some left over from yesterday. Right? Because we didn't get to do much in last class, right? So did you have a chance to look at the homework project 3? If you haven't, take a look at that. Essentially, I want to try, write a simulator which will go through and simulate some of the different memory allocation policies that we look at. But I think the most important part is there's a tool called PIN, which gives a trace of all the data that was accessed by your program, right? And that should give you a sense of what your program does, and you can play it with different applications, different programs that you write, to get a sense of what your programs typically do. And that, I think that's a pretty powerful thing, right? And the offer of, if anyone wants me to go through debugger, it still stands, right? So if you have anything, let me know. So before we go into the memory module, I want to give a sense of what we are trying to deal with, right? So consider this simple program, right? It's awful because it doesn't do anything useful, right? But it has some of the stuff that we want. It has a global variable. It has local variables, and some of them are initialized with when you allocate a new chunk of memory from somewhere. And it has loops, right? It has loops where it has to keep doing the same thing over and over again. And it calls system calls, right? How many of you taken a course in compilers before? Okay, so when you take a course in compilers, essentially you are trying to make sure that you convert this program in C to something that can be run on the real machine, right? And that involves converting it into the assembly language or machine instructions for the particular architecture, and also doing something with the operating system, which is what we are focusing right now, right? So the compiler would convert all these things into assembly code, but what the compiler may not know is what to do, where to put this stuff, right? And we kind of talked about this way when we started the course, that you have certain sections of memory, right? And I denote them by certain boxes. And I'm not saying where they are, what they do, but essentially you have some set of instructions here, and you have notions of hash and stack, and the arguments for the functions are usually allocated in the stack. Arguments for if you do a malloc, usually comes from a hash. But regardless, from application perspective, you have these notions of a lot of memory. And when you write a program, so when you have a loop here, right, somewhere in the instruction code, it will have something like a assembly language jump or something, right? Some sort of assembly language instruction to jump back. So it has to know where it has to jump back. So it needs to know what this address is. It needs to know where it should jump back. It needs to know when you access pointer that something should be pointing to some other location. So you need the addresses. You need to know how to access these objects, right? So those are the stuff that a compiler writer needs to know, right? Then there are other two concepts which are important, and we'll see in a little bit slide. But the idea is, when you compile this program, right, you convert this into a object file, right, which is essentially all the machine instructions for this particular program. You need to link them with other libraries. For example, explicitly use the standard I/O libraries here, and there are other libraries that are used by a program. So it has to be linked. What that means is, when you write this, when you have this square box, it should also have the code for printf, maybe from a library. It's linked into this program, so your program now has the code that you wrote and all the libraries that are out there, and it's linked in, right? So the notion of linking in links in all the libraries, so that when you call printf, the code for the printf comes from the library into your program, right? And the linking can happen statically or dynamically. Statically means it's kind of attached to your program, so you have your own copy of printf for all the programs. And most modern systems do not want you to do that, because most of the applications use certain C library, so you don't want to link the C library n times over. So what you have is, you have a notion of a dynamic linking, where you have some kind of a dynamic load area, right? And you have printf here, and it has to be linked into a program. So whenever your program calls printf, it knows that there is this printf function which is somewhere else, and it's all linked in. So when your program starts to run, everything is finished, right? So the OS's role is to make sure that this is allocated, this allocated, this allocated, this is somehow done, and when OS is finished, the application should just go, right? So it creates all this memory and stuff so that it may be linked in dynamically on the fly. It may be linked in while you're compiling this program, right? It has to load. It has to define a notion of a load where somehow from a disk or something, it puts all the code here, and it has to do this, right? It has to assign these constants and stuff. So loading is a process of making sure that your program is all ready to go. Linking is a process of linking all the libraries and stuff. So once the loading and linking and all those phases are done, your program should be ready to go. And if the compiler knew exactly how these memory allocations are being done, then it can generate the proper code for the whole system to work, right? And that's the role of the different pieces. So compiler generates all the code, and your program, as a programmer, you write the logic, and as OS, we'll make sure that we'll create all these little square boxes wherever they are and how they're addressed, and we'll make sure that they are protected so that you cannot change the printf that another process may also be using, right? So as we go through, if you look at the chapter, it kind of goes through different techniques. I will do this, we'll do this, we'll do this kind of stuff. But I want you to put that in a larger context of where these all fit in, right? And hopefully it'll be more clearer as we go along. So is this example sort of clear? So. And the reason why we do all this stuff is, the basic reason being that the faster some memory is, it's more expensive. And so you tend to have a little bit of those, and the cheaper things are you tend to have plenty of them, and they tend to also be slower, right? So you have the notions of, so when you take a hardware course, you have this notion of memory hierarchy, starting from registers to cache, L1, L2, L3, what have you, main memory, and then hard disk. So in terms of, so as you have faster and faster processors, the gap between all of these things keep increasing, right? So when you talk about registers, they should be able to keep up with one instruction per clock cycle. So if you have a 4 gigahertz processor, you should be able to go at 4 gigahertz because that's the most basic operation that the processor will do. And as you go to L1, L2, L3, you may need 2 or 3 instructions to do one operation for L1. You may need, like, say, 10 for L2, 50 for L3, and so on. By the time you hit a hard disk, you are at the ratio of 1 to 1 million or 1 to 10 million. What that means is, to get 1 byte of data out of the hard disk, the time it takes, you could have run 1 million instructions within the processor, right? So if you're going at 400 gigahertz, and roughly speaking, if you take a hardware course, you have a notion of CPI, which is instructions per cycle, right? Assuming it's 1-to-1 ratio, that means you can do 4 billion instructions per second. And if you're running off of the hard disk, you have to divide that by 1 or 10 million. So you're essentially going at 400 instructions per second or something. So if you're not careful, if you have to go to the disk, you can see up to a million factor slowdown, right? So you don't want to do that. So that's the goal, the performance aspects of it. And there's also the aspects of functionality aspects of how do you make these things happen, right? So the first thing is we need to bring the process into main memory and run, and that's the process of loading. So here's figuratively what I said, what the compiler would do. So you wrote the source program, right? You first invoke the compiler or assembler or what have you, and they convert that to object code, which essentially converts your C program to the instructions of the lower hardware, right? And then you have to do a linkage editor where you link with all the other libraries. So it could be static libraries that you wrote or libraries that the system provides, like C library or pthread library and so on. And then you have to load them, right? You have to load them, essentially creating the proper structures to put them into main memory. And while you're loading, some of the system libraries may be dynamically loaded. In fact, most of the modern operating systems support what they call DLL or shared libraries or what have you. And once it's all done, once all this phase is done, you have something like this in main memory, and your process can go, right? And don't forget that the OS is still involved with the process scheduling and stuff. So once it's all done, then the process scheduling part decides whether you should get the CPU or whether you should go out. But at the end of all this process, something like this should be somewhere, right? So in terms of the binding, right? So in terms of figuring out that you are, let's say you're accessing this, right? The j equals 10, and somehow the compiler put the 10 here, and when you access this j, it has to read this particular location, right? It could be done at compile time, meaning so if the compiler knows exactly how much memory you have, what your memory is going to be, it can make it all simple by creating code where all of this it's already known. So it can say this is 0 and this is 1000 and this is 2000 to 2500 or so. So when it creates a code, it's statically connected such that j happens to be at the location that it knows it should be, right? What that means is once this program is compiled, once it's run, it has to run on that particular machine with the exact same parameters. You cannot change any of the parameters, right? If you add more memory, your program won't be able to use it. If you have less memory, your program would fail because it's expecting certain things to be at certain locations, right? But it's simple. I mean, once you do this stuff, it's all laid out, it's all there, right? Can you imagine a scenario why you would use something like this, where you have no flexibility whatsoever? You have to run the exact processes as they were designed for, right? You can't run a new application because if you run, then the addresses would all be messed up, right? Yeah.
Maybe in embedded chips.
Yeah. Most of the embedded chips, and even your cell phones and PDAs and stuff, they could do something like this, right? It's simple enough that they may not have all the stuff that the hardware will see you would need to run more complicated stuff. Essentially, you don't have a memory management unit. So essentially, if you get a cell phone, it's designed to operate with the same amount of memory that you have. You add more memory, it can't use it. If you take out some memory, it'll crash, right? But it's simple, right? The other time is you create these code, like whatever the code, assuming you don't know the exact precise locations where they should be, right? And when you do during the program loading, the OS tells you that, okay, you're going to be running from this is 2000, right? So do everything relative to that whatever number I give you, right? So when you do a jump here, you don't jump to a precise number. You say jump to whatever the OS gave me plus something, right? So this happens to be, if this offset happens to be 200, you will say, in the first case, you will say, I'll jump to, in the first case, I said this is to 1,000, right? So you will jump to 1,000 plus 200, 1,200, which is part of the code. In this case, you'll jump to whatever the OS gave you plus 200. So the OS gave you 1,000, you say 1,200, OS gave you whatever. So the OS has flexibility in figuring out where to place you at load time, and all the instructions are changed at that point. You can't do anything else after that, right? Once it's done, it's done. So when you're loading it, you tell what the addresses should be, and that's it, right? And that's more flexible than the compile time, but not as flexible as the other module, which is execution time, which states that every time you execute something, you have to do this addition. So every time you want to access this location, you have to add it to some variable. You have to do some calculations, right? The last one has the most flexibility because what that lets the OS do is it can move you from here to somewhere else, and you won't know anything different, right? Because it basically says anytime you want to access anything, any instructions, anything with the memory, you have to offset it with something that I would set you, right? And so you don't know where you're going to be, but you know that if you keep adding, you should be good, right? So before I show figuratively how that looks like, Staying a little bit on the in the case of the how the compiler does the loading and linking, right? So in the case of a loading, there's one way is to either do it statically. So when a program starts, it loads all the libraries, everything that your program can want, or you can do it dynamically, right? In the dynamic mode, so when you touch some instruction, something happens, and then those particular functions are loaded, right? So for example, when you write a program, a big program with lots of error checking codes, there's no point in loading all the error checking codes, right? And for example, if you load a program and it can operate with a PS keyboard, USB keyboard, and USB mouse, and all those things, there's no point in loading all of those, right? You only have to load whatever is there. And if you don't have particular code, right, we'll see how these things would be noticed. Essentially, the OS can get you a trap, and then you call a user program which does this loading, right? Which you tell it that you're going to be loaded in this location, and the loading happens, right? With the dynamic linking, right? So dynamic linking says that this printf, right, could be linked in from some area which is already allocated, which is being used by somebody, right? So you don't know where this is going to be. So when your program starts to do this printf, it has to go to the OS and ask it, I know you have a copy of printf somewhere in your system. Tell me where it is, and I want to link to it, right? The way you do that is when you compile your program, this printf is replaced by a stub routine, right? Which basically does all the things we just said, which does the dynamic loading, right? So when your program comes here, and the first time it sees this stub code, it'll run the stub code, which will basically ask the OS where the library is, find out what the address is, and it'll change its own instructions to link to it the next time, right? So your program actually morphs. Right? So if you go through a debugger and look at what the instructions of your application is, before you call printf, your system will have a different function whose goal is to call the system to figure out where these libraries are loaded, and if it finds out where the address is, it'll replace this code to call this library directly, right? So when you go through a debugger, before this linking happens, you see a stub code. After the linking happens, your code will be replaced, right? Otherwise, you won't know any difference. Otherwise, if you don't have a debugger, your program always looks like it's operating fine. But essentially, when you hit the code, you'll do the stuff and it'll load these objects, right? And those are mechanisms by which you can do this stuff, do this loading and linking on the fly, right? Once that is done, you have one copy of printf for the entire system. So every program in the system, for the most part, will use that one library. And we'll see how it's protected such that you can't modify this code, right? So if you protect it properly, then you can't modify the code. You get good memory efficiency, and you get the same code. Yeah.
So you compile your program with a stub code, and then at execution time, you replace the stub code with the linked library?
Yeah.
Okay.
So it sounds kind of ugly, but that's a quick hack that works, right? It's kind of ugly. I mean, you shouldn't do that in your code. I mean, you should not replace your code with something else on the fly. But these things work because these are properly debugged and stuff, right? How many of you know that you can actually change your program on the fly by writing your own code on the fly? You guys know, right? So you can do something like this. I'm not going to go through the exact syntax, right? Because it's horrible, right? So you can say star ptr equals, like say 10 star pt, like 20, right? I'm not saying what the 10 and 20 is, right? But 10 and 20 are supposedly machine instructions that you know, right? Then you can actually call ptr with the proper stuff, right? You call ptr as a function, right? So you created this piece of chunk of code. You somehow filled it, right? You can do it nicely, or you can do it hackishly, and you just do this, right? Essentially, since C lets you cast a pointer from data to code, all that, whichever way you want. So you can call this function that you just created, right? You'll complain that this may be bad, but like most things with C, you can ignore them, right? So once you do that, you can run this as your piece of code, right? Don't ever do that because you have to be exactly clear what these things you're doing here are, and this is a really ugly piece of code, right? But that's sort of what this is doing, but this is acceptable because this is being done by professionals, not by normal people. Yeah.
In the library that you're linking to, is the code there stored as machine code?
Yeah.
Okay.
Yes, it stores machine code with any references that it does to its own library as relative addresses, and it could call other libraries, right? So there are other libraries. So within your OS, there's your kernel, and there are all these dynamic libraries which are loaded, which are shared by a whole bunch of systems, right? And you can see the incarnation of this. So if you in whatever operating system you're using, if you try to look at how big your program is, right? How big your Word program or something, it tends to be fairly large. I mean, your most of the Word and PowerPoint, all those things tend to be fairly large. Let's say they take 1 gig of memory, right? But you can run many of them in your system, but you don't need like 5 times whatever each one individually says, right? Because they're all shared. So actually, you'll have a column which says what is you want and what is actually allocated, right? And actually allocated does not include these things which are shared because they are shared among a whole bunch of stuff, right? And it operates on the notion that most machines use a standard set of libraries. All PowerPoint, all the Microsoft products typically tend to use a few libraries. So you don't have to link them all. You don't have to have a local copy of all of them, right? I mean, the exact semantics and all those things are way beyond the scope of this class. It's more of what you do from compiler class. If you are curious, use your compiler to say create a static library, static program, right, with no dynamic linking, right? And you see your program suddenly go from some small size to like a really large program, right? Because it has to load everything into one stuff, right? So one of the things that, since you have a notion of multiple processes, right, except for the compiler time loading process where you have to know where every exact location has to be, dealing with the physical addresses for your application is going to be horrendous. Dealing with one address where the OS and you are having the same number would be horrendous. So what you end up having is logical addresses or relative addresses, right? Logical addresses say that there may be many applications. From your application perspective, always consider addresses start at 0 and go on up to whatever the machine can address, right? So if you have a 32-bit machine, it can address up to 2 power 32. So you assume that each process gets its whole 0 to 4 gigabytes worth of data, right? And the OS will make sure that whatever has to be done would be done underneath you. But from your perspective, you only deal with this one address which starts from 0 to whatever, right? So OS will make sure that when it moves you to some different location for whatever it is, you'll have to do the translation from logical to physical, right? And it has to do it for every instruction that you do, every time you access a memory location, right? So though it's convenient because you don't have to now know the exact physical addresses, if you add more memory, the OS has a lot of flexibility in moving you or taking in new memory and all those things, you need hardware support, right? If you don't have hardware support, so essentially, I'm jumping 2 slides ahead. Essentially, this is what happens. So you have a logical address, and the OS now says, I will make sure that I'll translate that to whatever the underlying machine can deal with, right? And the simple way to do that is to add something, right? So it can say, you are creating a logical address of 346. At this particular instant, I moved your chunk of code where you assume that it starts from 0 and let's say go to 3,000. And you're somewhere accessing this chunk. I have moved it to in the physical memory, I have moved this chunk that you're accessing here at 1400, right? So when you think you're accessing 346, you are really accessing from here plus 346, right? So that way, your program always thinks that it's accessing 346, and in this particular instance, you're accessing 14346. And the OS, if it finds that it needs to move you to 28,000, your program won't know a difference, right? OS has to move you and do all the stuff, but from program perspective, you don't know the difference as long as that particular register is always filled, right? So it's the OS duty to make sure that the relocation address is always correct, because if it's not correct, then you're going to be accessing something bad, right? So should an application know that there's a concept of relocation address at all, register at all? Do you think it will know what it is? No, it shouldn't. It shouldn't be allowed to touch it. You shouldn't be allowed. You can let it see it, but it's no use, right? The application cannot. Application, all it knows is the logical address. It doesn't know what the physical address it is in, right? So from an application perspective, you never know which physical address you are actually in, right? And you could know that, but it'll keep changing, right? Yeah.
I guess I was just a little confused about why you would want to move around your various programs in physical memory. Is it just because, like, if you've got a program that, say, is going to take up a variable amount of memory and you're going to start crashing into somebody, you're going to start overwriting something else? Mm-hmm. Is that why the operating system would want to move you around? Or?
So I'm going to jump like way ahead into the course, right?
Talk about it.
No, so a simple example is, I mean, there are a lot more reasons, right? But let's say if your machine has 1 gigabyte, right? If you're not allowed to move anything, if you're not allowed to change anything, the maximum application you can run is 1 gigabyte, right? Because if your application uses all the 1 gigabyte, you can't do too much, right? But if you want to run, like, say, 10 1 gigabyte applications, right? You may have to reuse the same memory over and over again, right? So you could say all of them have to use the same address over and over again. But if I have the flexibility to move you around, then two applications which think that they're operating on 346 may coexist because I moved one of them here, I moved one of them here, right? And they're accessing something here, they're accessing something here. And later on, a third application comes in, it wants all this memory. I can throw both of them out, move another application. So I have a lot more flexibility in moving applications in and out, right? Because now the OS is completely in control, because the applications, all they expect is when they run, your relative address should be same. But the OS can move you around because there's a new application which needs all the memory. There's a small application, there's many applications. And we'll see a whole bunch of reasons why we get to move, right? But it gives you all the flexibility to do a whole bunch of nice stuff, right?
Okay.
Yeah.
In C++, when you use pointers, do those refer to logical addresses or physical?
Logical. Nobody should be able to see the physical address except the operating system. Okay. Only the operating system can address anything in physical address. Only the operating system can know about physical addresses, right? There are some things that can only be done in physical address, right? So, for example, so one of the ways to do I/O is through memory mapped I/O, right? So here, what you say is you have this. Let's say this is your entire physical address, right? Anything you write into address location 100 to 120 is really going to this network card, right? And that's called memory mapped I/O, right? And that's a hardware feature, right? Where it's not actually writing into memory. So the hardware makes sure that if a processor writes into 100 to 120, whatever you write there actually goes into the network card. Whatever the network card writes, if you read from here, right? But there's no actual physical memory there. I mean, this is all done by the hardware, right? The hardware makes sure that from a processor perspective, it looks like I'm writing it to 100, but there's actually no memory there. And through some magic of hardware, it actually goes to the network card, right? So that's called memory mapped I/O, right? And those always happen in physical address space. Those do not happen in logical address space. So the OS has to make sure that if it has to talk to the particular hardware, it'll write something here, and whatever it reads, it'll read it and then copy it into the user application, right? So there are conditions like this where you have to deal with the physical address, which only the OS is allowed to do. You have to be in the privileged mode to do that, and only the OS can do, and it does not know. From an application perspective, you guys have never seen physical address, right? So when you use the pin tool for the homework project, which tells you all the instructions that your program acts. So the pin tool is a really nice tool. It basically tells you all the instructions that you're accessing. It tells you the instructions that you're going through, right? It tells you in this instruction what addresses you're accessing and all the data that you're accessing. So if you're reading something, it tells you, the source and the destination. If you're doing a write, it tells you the source and destination, all the addresses, right? So you can kind of go through that to see what your program is doing. So if you do the matrix multiplication, you can see what addresses are being accessed by each of the instructions, right? And however, all the instructions are logical. You can't find out what the physical address is. Even if you can find the physical address, it's completely meaningless, right? Because across each instruction, the OS can come in and change where you're going. So it may look like you're doing, if you're accessing an array, right? You say for I equals 1 to 10, you're accessing this stuff, right? So you expect the first one to be address, let's say 1, second one to be 2, 3, 4, right? If you're looking at it from physical address space, you may see something consecutive like this, or you may find something that, 1, and then the OS moved you around to a different location, so now you're seeing 202, and now you're seeing 3, and so on, right? So depending on where the OS moves, so it's meaningless. Yeah.
One more thing too, on the relocation register, is that value is determined by the operating system,
Yes.
right? And is that the kind of thing that you'd maybe keep in like a process control block?
Yeah. Yeah. So the relocation address register value, the OS has to keep it. Probably keep it in the PCB or whatever data structure, and only the OS can deal with that. So if the OS ever forgets that value, you're toast, right? Because now you are so. Because OS is doing all this tricks, so let's say it's assigned you here and me here, right? And this allocation. So when you're accessing the relocation register has to be this, right? If by accident it gave you this, then everything is lost, right? Because now we are operating on my program and not your program with unknown results, right? So this is the basic functionality of the OS. So usually you don't see bugs in this particular code. If you have, then you're not going too far, right? I'm going to go back to the previous slide. So the hardware to do that is called the memory management unit, right? And most of the modern machines, like your desktops and stuff, have to have a memory management unit because this operation has to be done for every single step. So if you have to do this in software, right? So for example, if you were to do some code like this, right? Let's say you're doing this in C, right? So this will have to have an address. This will have to have an address. This will have to have an address because these are variables. These are somewhere in the memory, right? To run this instruction, you have to find out what this address is, right? Whatever the logical address you want, plus relocation address for that particular address to get the physical address, right? So you have to do, so this essentially would translate to logical plus physical equals logical plus physical plus logical plus physical, right? So what used to be one addition now becomes, there's one addition for each of these operands, right? And as you can imagine, your program can get extremely slow, right? So this has to happen in hardware. If you don't have a hardware, this is not a viable option, right? And that's one of the reasons why you do this only for, if you have a memory management unit, then you can do all this stuff. But if you have a cheap device like your cell phone or some of these, like a remote control or something, you don't want to put this kind of a memory management unit. So you can't afford to do all this calculation in software. So you're forced to have the code in static locations, right? But these tend to be cheap from a desktop perspective. So most desktops come with the MMU, right? And you use that for other stuff, like you use that for doing I/O and stuff. Because memory management unit can do other things while it's not doing this addition. So it'll do the relocation and some of the other stuff, right? But what I want you to take away from this slide is what the hardware does and what the software does, right? And that's the key, right? The OS is the only one which can manage what contents go into the relocation address. Once the OS puts something in, OS gets out of the way, right? Once the relocation address is set, then the application can go on its own merry way, because now it's between your application and the memory management unit, right? Memory management unit uses whatever the OS puts in there, and it does all the translation till some event happens. So the OS is not involved when your program is running usually, right? Your memory management unit is involved in every instructions, but not the OS. It only comes in. So when you do a process swapping, you have to make sure that all the relocation registers are saved and all the new relocation registers are stored or what have you. And after that, the OS gets out of the way. Yeah.
What does the MMU look like at hardware? Is it a bunch of registers, or what is it? What is it contain?
I actually don't know.
Okay.
I mean, I think I would suspect it has a addition unit, right, and bunch of registers to do this stuff, right. So it's a specialized CPU which all it does is do this translation.
Okay.
But it looks like any other small chip, right? If you open your PC, it traditionally says MMU on the thing, so you may be able to see that, but it just looks like any other CPU, right?
Okay.
So it's not doing anything complicated. All it's doing in life is adding whatever relocation register with whatever address which comes on the logical address and finds a new address, right? And actually does more in terms of doing the translation for caching and all those things. So if you take if you have you guys taken the hardware course, or is it?
Taking computer architecture 1.
You're taking computer architecture 1, right?
Yeah, we're taking 2 right now.
Okay, so you must go through that stuff there.
Not everyone's taking computer architecture too.
Okay.
This computer architecture 2, we're kind of dragging our feet with cache and virtual and pipelines right now.
Okay. I mean, that's the stuff, right? I mean, so if you're taking compact and if you're doing caching and memory and all those stuff, right? Essentially, this is the one which is kind of gluing. This is the one which lets the OS talk to the hardware stuff, right? OS does not know a whole bunch of stuff about caches and all those things. Those are the magic that the hardware provides. But OS is involved in setting these flags. So then you have the other concept which is useful, and we'll use that later on too, is the notion of swapping, and that kind of answers some of the things you're mentioning, right? So since the physical memory tends to be a lot smaller than what you would want, I mean, you never have enough physical memory to run all the applications, right? So one of the ways to make it look like you have a lot more memory is to do this notion of swapping, right? So when your application is running, you get all the memory that you want, and when you're not running, I swap you, basically put you to a hard disk or something. I move you to a location where it's traditionally cheaper than where you are, right? So you don't move you from main memory to cache. I move you from main memory to disk or tape or what have you. And so the goal here is I can move in another application. So when I do a context switch, when I go from one application to another application, the previous application which is being booted out can be booted out completely in terms of moving all the stuff into disk, and then you start the new process, right? And as we'll see, that there are a lot more complicated ways we'll look into doing this, because if you're swapping all of them en masse, then you're going to wait for a while for the disk to finish writing. So you only do them, you interleave them, you play tricks on what you get to write, what you don't get to write. But the general concept is whatever you don't need, you move it to the hard disk, and then you bring in a new one, right? So when you bring the process back, you may not have the memory that you had before, right? And there's another reason why you have to do this relocation, right? So suppose you happen to be on location 1000, and I had to swap you out. When I want to bring you back, 1000 may be used by somebody else. So either I move the other process so I can make the same space available for you, or I move you somewhere else, right? And swapping, it's a lot easier if I can move. It's always nicer for the OS if it can move, if it can do whatever it wants to get the performance, right? As long as the hardware is there to support it from doing the stuff, right? And conceptually, this is what you do. So you move a process from your process to the disk and so on, right? without going into the details, we'll see a little bit of that later. Can you do this for the operating system? Can you move the operating system code also to the disk? All the time, some of the time, not at all. Yeah.
Would that be where it is like initially stored, so when you turn on your machine for the first time, it would load the operating system stuff into
Yeah.
memory?
But afterwards, can it move the operating system out to somewhere else?
Does it depend on your OS?
It depends on the OS, but
Doesn't, I mean, it's just going back a while, but DOS like overwrote the operating system in memory, right?
No, it's not hideous like the DOS stuff, right? So what I'm saying is, you move the whatever constructs in there into the memory, right? You're not rewriting. Let's not talk about DOS, because DOS is not an operating system, right? I mean, DOS was doing something so horrendous. It's kind of hard to learn any principles out of that, right? Like what do you do for processes, right? Can you move the OS kernel? So if you want more memory, can you kind of make the OS smaller, right? And we'll see a little bit later some of the stuff. Some of the things are easy to do, and some of them are not, right? So if you have a code which is doing the swapping, so inside the kernel there's some code which keeps track of where these objects are, and it stores it in the disk and brings them back. You can't swap that out, right? You can't swap the data structure which keeps track of what is out there in the disk, right? So there's some data structures which cannot be swapped out. There are others which can be swapped out. If there's a error code or something, it can be swapped out. And you don't actually do it naively all the time. So as some of you kind of sort of guessed it, like if you have an application which is on the disk, right, your program, right, since you don't change the program on the fly, you don't have to swap it out. You can just read it back in, right? If you have your program can be read back in without actually having to be returned back, right? Whereas your data may have to be returned back if you modified it, right? So we'll see more complications why you don't want to do this all the time. Always remember your disk is extremely slow. Compared to what we're talking about, your disk is extremely slow, right? I mean, it's million or so times slower. So you want to avoid that as a plague, because if you have to wait for the disk, your system is very slow, right? So there are, conveniently, I had like something, the more complicated form of allocation, which is all these square blocks are kind of hanging, floating in the air, right? That may be one way of allocating stuff. The other way is so for your process, you get this big chunk, right? And you call this heap, and you call this the code or text, right? And you call this stack or what have you, right? So I have this one chunk given to you, and you kind of manage these things amongst yourselves. Or I can give you these things as this free hanging stuff, right? Free hanging stuff is more general than this one. You want to guess why you prefer that one to this? Yeah.
Well, maybe you don't have one big chunk of code, but you have a couple little, or one big chunk of memory available, but you have a couple little chunks of memory available. Then something like that would be better than.
Yeah. So you don't have to get this big chunk of code, right? And we'll say the OS can still play games to make it not so bad, but yeah, that's one reason, right? The other reason is they can independently grow, right? I mean, if you did this, then the heap can't grow past this boundary, because you're already using this particular location for something else. So if it grows, then your program usually doesn't work, right? So you may get errors like out of heap or something because you can't grow anymore. Whereas if you have something like this, each one of them can independently grow to a large extent, right? And especially when you have dynamic loading, that's hanging out anyway. That's not part of your application anyway. That's in a separate kind of stuff. So you kind of force the model. So anyway, so if you look at the single partition model for your process, you have one relocation address, right? And that makes life easier, because essentially when I swap you in, I have to set this one relocation address which addresses all the stuff that you may want, right? So most of the modern MMUs will also have a notion of a base and a limit register to make sure that you don't trample on somebody else's code, right? So when it stores the location address, it also stores the base and the limit address, which states that anything beyond those addresses, you're not allowed to go, right? So you may have the location address here, but the base and limit. So essentially what it does is, every time it generates an address, right, it has to add the location address to the to your logical address, to get the physical address, and then it has to see if they're between those two limits. If they're not, then something is wrong. It'll kick it back to the OS, right? So every instruction you do right now, your CPU creates an address, and you have to see if it's between those two limits before you do the addition, right? So MMUs add more functionality as we go along, like going back to your question. And one of the stuff is, this is a simple way to give protection, right? So it basically says that you cannot go beyond the base and the limit, but within that, it doesn't say too much about what you can do, right? And later on, we'll see that there are ways to make it even more powerful by saying this chunk of code can only be read or written or executed and what have you. But you have this kind of stuff. And again, those limits have to be set by the OS, right? Because the hardware does not care where you run, but the OS has to care that these are processes, because process is a concept of the OS. It has to say this is one process, this is another process. You shall stay within this and this limit. You shall stay within this and this limit. If you try to go beyond that, then you get a trap, right? So what would happen if you get a trap? So have you seen a condition where your program accesses some address which is out of the stuff? Have you seen the OS communicate that back to your application? Yeah.
Is that what a segmentation fault is?
Yeah. Essentially, it's a segmentation fault, right? It says you're outside your segment. If you think of that as a segment, it says you're accessing something outside a segment. Deal with it, right? You can catch a signal and do something with it. The default condition is your process is killed, right? But you don't have to be killed. You can actually take action for that. So the notion of contiguous allocation. So if you do multiple partition, then I can. It's sort of what we defined here. So I can move these things around. I can allocate for the same application. Different pieces of code can be allocated in different location. I can move them around, what have you, right? And so if a partition is allocated, it's in the blue here, and if a partition is not allocated, it's free, right? You have these holes, and when you have applications coming and asking for new chunks, you give them as they are needed, right? So that brings up the issue of dynamic storage allocation. So you're trying to allocate whatever you're asking with whatever free space is out there. So it always has to keep track of what is allocated, what has not been allocated, right? If it ever forgets that, you're toast, because the OS has to know. It's the OS concept to know what is allocated to a process, what is not allocated to a process, because process is the OS concept, right? And three policies you can imagine is the first fit, best fit, and worst fit, right? First fit finds the first free space, puts you in. Best fit finds the best place for you to fit, which will leave the smallest amount of free chunk, and the worst fit will find one which leaves the largest amount of worst free chunk. And best fit tends to create lots of small holes, and worst fit tends to create lots of more useful stuff, right? But you have to do the searching to figure out where your memory should happen, right? And as we progress, we'll see there are better ways to deal with some of these constructs. And I'll repeat this again in next class. Essentially, what this creates is a notion of external and internal fragmentation, right? External fragmentation is something that is beyond your process, unused space. So for example, if you go back in the previous slide, you have the gray stuff, right? Which is external fragmentation because it's not being used. Hopefully you want this to be useful to somebody else, but if you created such a small thing that nobody else can use it, that's a problem that you have to deal with, right? Internal fragmentation happens when you ask for, let's say you ask for 1,000 bytes, and the OS says, I can't give you 1,000, I'll always give you 1,024, right? So even though the OS thinks that you have 1,024, you as a programmer only want 1,000. So you have something which is internal to your own process, which is unused, right? And that's called internal fragmentation. external is something that the OS knows, but it can't do anything about, right? And we'll repeat this again in the next class. Yeah.
I was just going to ask, is that kind of like what's going on when you run a defrag on your like hard disk? Is it
No. So that's for the hard disk stuff. It's similar, but that's vaguely similar, right? Yeah, that's a good question. So you'll notice that for the memory and the hard disk, some of the stuff are the same, but I'll try to tell you what the real difference is when you go from one to the other, right?